Hi, I'm Zor. Welcome to Unizor Education. So basically we are continuing talking about Lagrangian and its implementation, its usage, etc. But I need certain amount of mathematics to go further. Now my next step in Lagrangian's analysis will be Lagrangian in generalized coordinates. And for this I need some math which I will refer to, and I would like to basically dedicate this particular lecture to all these little tools which I will use when we will discuss this generalized coordinates. So it's just a few simple things, but it needs to be basically discussed separately so I can refer to it in the future. Now, this lecture is part of the course called Physics Plus for All, and it's presented on unizor.com. I suggest you to watch this lecture from the website. You go to unizor.com, then the course Physics Plus for All, and the chapter is Lagrangian. Now, it has some other preliminary chapters like variations, for example, which we also need. But in any case, this is the general direction, and I do suggest you to watch it over there, because not only the video you will have there, but also just on the same screen you will have video and the textual part. Textual part is like a textbook, and I do recommend you to watch the video and read the text in any order, whatever it's convenient for you. Okay, so this lecture is about mathematics, which needs to be addressed before going any further with Lagrangian in generalized coordinates. So I have a couple of lemmas and a couple of logical discussions, so to speak. Now we are talking about any function which basically depends on certain other functions. Let's say q1, q2, etc., qn. All of these internal functions are functions of some variable which I call t. Now, what is this from the physical standpoint? Well, t is time, and q1, q2, qn excuse me, are coordinates of some point in some n-dimensional space. Now, what is function s? Is whatever the function of these coordinates is. Maybe it's energy, maybe it's magnitude of its speed, maybe it's whatever. So we are talking about any function of coordinates, and coordinates depend on the time, which basically means this particular function as dependent on time ultimately, because if time is given, then these functions are also given, and they basically define the motion of this particular point in n-dimensional space. So these functions define the motion, so we know the position, let's say, at time t. This is q1, q2, qn, and that's why we know this function. Let's say it's a kinetic energy at that particular time, right? Now, about this function, I have a couple of theorems, basically. Lemma. I call it lemma because they're very tiny, tiny theorems. Now, the first lemma is the following. If you will partially differentiate this function s by coordinate qk, and if you will take a time derivative of this function, which is also basically depends on all the coordinates and their derivatives actually by time, and if you will partially take a partial derivative by time derivative of this particular coordinate is the same, the result will be the same. Now, first, how can it be explained? Well, you might actually remember there is a theorem in the theory of limits, when if you would like to have limit of, well, let's say sine of x divided by x as x goes to 0, you can replace the ratio of two functions with the ratio of their derivatives, cosine x divided by 1. Now, this doesn't, we don't know what this is because it's indefinite thing. It's 0 and this is 0. But now if you will put 0 here, this is 1 and this is 1, so this is equal to 1. And indeed, the limit of sine x over x is 1. So the ratio of function can be replaced in the limit case with ratio of the derivative of these functions. Basically, that's exactly what we are doing. These are two functions, differentials basically, and these are two derivatives correspondingly of these things. They must be equal. Let me give you an example. For example, s of two functions, I will, instead of q1, q2, I will use u and v. Let's say this is equal to u square v plus v square, just as an example. Now, if you will do ds by du, what is it? Well, this is a constant, so it's just basically v times derivative of 2u square, which is 2uv, right? 2uv. Okay. Now, if you will take the derivative by time, well, derivative by time of this thing is what? First, you have to, well, if you have a derivative by time and you have a function which depends on other functions, it's a chain rule, right? So first, let's do it by u. So that's 2u and u derivative by time times v. That's basically derivative by u and time plus derivative by v. Now by v is, well, derivative by this v is u squared because it's a constant times v plus derivative by time of 2v, it's 2v v derivative. Am I right? And if you will derive, and you will partially derive by du, prime, so you will have what? This 2uv, which is the same as this one. And the same would be if you will do it by v. So this is just an example, but let me just prove it in a general case. All you have to know is how to take the derivative and partial derivative of the function which contains more than one other functions which it depends on. All right, so if so first we know what ds dsq is. So let's just think about what is derivative by time of s. Well, again, this is the function of many other functions, so you partially derive by each one of them and then multiply by its derivative by time. So it's a sigma ds by dqi, sigma for I, times derivative by qi by time, which is qi apostrophe, right? So basically it's a function of all the q's and all the q primes, right? Some kind of a function. So now, if we will, if we would like to have a derivative ds prime by dq by dq prime. Now this is the sum of many different items, Now, qi and qi prime are basically like two independent variables, because we are partially deriving only by qk prime, which is only one particular item in this sum, the one when I is equal to k. And the derivative by qk prime would be this coefficient, which is ds by dqk, right? When I is equal to k. So this is the coefficient, and we are basically doing partial derivative. And that's what we need to do, to prove, basically. So all we need to do is just represent the derivative by time of the function s as the sum of partial derivatives, and using the chain rule, derivative of the function qi as a sum. And only one, when we are doing for one particular parameter k, from all the sums, they are all independent of qk prime except one, which has the coefficient this one. So that's very easy. Okay, second lemma. Second lemma is about changing direction of differentiation. Now, under a very very broad condition, if you have a function of let's say two arguments, let's say f of x of, don't really need even that, but f and x, then derivative of f by dx dy is equal to second derivative by dy dx. So you can so you can change the direction of differentiation. Sorry about my voice. Okay. Now, under very broad condition, this is true. It's called a Schwarz theorem. I'm not going to prove it. I'm going to use it. Proof is basically not very difficult, but I just don't want to spend time. It's a basically textbook theorem in calculus. So I'll just use it. But in this particular case, situation is slightly different. Situation is, as you see, we have a function which depends on functions of t. But in this particular case, the theorem which I'm talking about is the following. If I will take a partial derivative by qk of full derivative by time, then I also can basically change the direction. It would be full derivative by time of partial derivative by qk. So it's also kind of change of arguments, but much more sophisticated than in the case of a Schwarz theorem. But I will use Schwarz theorem to prove this one. And how do I do it? Basically the same thing. So first of all, let's talk about this expression on the left. So it's partial derivative by qk of, now this is a full derivative by time. We are using again the rules of differentiation of combined functions. So again, this is a chain rule. So this would be sum of partial derivative by qi times derivative of qi by time, which is qi prime, summed by I. So that's on the left. All right, fine. So we are actually trying to partially derive it by qk. Well, again, q and q prime are independent right now. So basically the result of this would be, I can put derivative by qk inside the sum, and it would be, now these guys have dependency of qk. This guy is totally independent. It's one particular qi which doesn't, it's qi prime actually, which has nothing to do with qk again. These are functions and these are derivative by time of these functions. It's completely different things. So I have to really differentiate by qk only this part. So it would be sigma with 2s by qi qk qi prime. So it's the first derivative by qi, and then I added, I'm sorry, it should be the other way around. Usually the first one on the right and the second one on the left. The external one on the left. So that's qk. Okay, now let's talk about this one. Well, again, this is a function which have to be differentiated by dt, which means we have to differentiate it by each component as a sum. So dt of what? Of ds by dqk. Okay, so what is it? We are differentiating by time of this function. So that's sum ds by dk. First we have to differentiate by internal function I, right? So that would be dqk. So we differentiate by I, by dqi, sorry. Second derivative dqi times qi by time. So now let's compare these two things. They are almost the same, except the order of differentiation is different. First we differentiate function partially by qi and then by qk, and in this case we are differentiating by qk first and then on the top of it by qi. And since we can refer to Schwarz theorem, under very broad condition, basic conditions are continuous of the derivatives are supposed to be continuous function. So this is equal to each other, so that's why we have proven the theorem. Okay, so these are just two kind of specific for physics of Lagrangian mathematical statements, which I will have to use in the future. So I will just refer to this lecture and consider this to be done. Now, next is something which is kind of cosmetic, I would say. So let's imagine that we have a system of n point masses in three-dimensional space. Now, these are basically every component of the system has three coordinates, right? So x1, y1, z1, x2, y2, z2, etc., xn, yn, zn. All of them are functions of time, of course. All of them are functions of time. So that's how we describe the system of n point masses and components in three-dimensional space. Each one has three coordinates. So all I'm doing right now is I would like to change the names of these coordinates. Why? Well, let's say we are talking about Euler-Lagrange equation for the system of certain number of certain freedom, elements of freedom. Okay, now we have proven in the previous lecture that for this system the Euler-Lagrange equations are equivalent to Newton's second law equation. So Newton's second law is F is equal to ma, so this would be vectors I and I, for each component. Now we are talking about conservative systems when f can be basically divided by minus du. U is the total potential energy of the system, well, obviously depending on time, by dxi, du dyi, and minus du dzy. These are three components of this vector, and each one of them is equal to, if I remember correctly, what was it? d per dt of kinetic energy by dxi prime. And here the same thing, d per dt of kinetic energy by dyi, and kinetic energy, regular d per dt, kinetic energy per dzy. So it's 3n equations. Now obviously I can do it differently. I can put, instead of u and k, potential and kinetic energy, I can put Lagrangian, which is L is equal to k minus u, in which case I don't need these minuses and I don't need this potential energy, but I can replace it with k minus u, would be L here, here, and here. It's all from the previous lecture, so I'm not really spending any time on this. Lagrangian, these are Lagrangian Euler-Lagrange equations. Now, what's the problem with this? I have x and y and z, and I have three, for each I have three different equations. Now, what I'm doing is purely cosmetic. I call this S1, S2, S3, S4, S5, S6. This would be S3n, this would be S3n minus 1, and S3n minus 2. In which case, instead of 3 for each I can write only 1 for I from 1 to lowercase n, which is equal to 3 capital N. It's exactly the same thing. These are Cartesian coordinates, S1, S2, S3n, or Sn if you wish, S lowercase n. So they're the same Cartesian coordinates. I'm not changing anything, just the names. Why? Because it's just kind of more convenient to deal with one equation, Euler-Lagrange equation, for each dimension than with 3 for each object. So it's easier to come from component with three coordinates to basically one single coordinate, which is called by the same name. Just a convenience, no more than that. And the last but not least of it I would like to discuss today is transformation of coordinates. So let's say you have one set of coordinates, S1, S2, etc., Sn. Let's call it just S without index. So that's basically what was before. Now it's easier for me to do it this way. Now let's say you have another set of coordinates, Q1, Qn, which are basically transformable from one to another. Let's say you have Cartesian coordinates and I don't know, spherical coordinates in space, or cylindrical coordinates, or polar coordinates on a plane, Cartesian on a plane and polar on a plane. They are convertible into each other very easily from one to another and back. What my point is, so if these are functions of time, since coordinates are converted into each other through some kind of function, let's say S is equal to capital S of Q, and Q is equal to capital of S. These are transformation functions. Each one of them represents actually n different equations. S1 is equal to capital S1 of Q1, etc., Qn, then S2, S3, etc. So, for instance, we are having deal with this thing. What actually it means? It means that the system is moving by itself somehow. There is a trajectory of each component of this system. Or if you wish, you have one point in n-dimensional system where n is equal, lowercase n, where lowercase n is equal to 3 times capital N, which is number of components. So in any case, there are a certain number of numbers and functions actually of time which we use to represent physical trajectory. But physical trajectory, no matter how we represent it using this function, set of functions, or this set of functions, physical trajectory is the same. So whether we are moving on a plane and using polar coordinates, r theta, or we are moving on the same plane and this is the same movement of the same particle which has two coordinates, Cartesian coordinates x and y. Functions are converted into each other. X is equal to r times cosine theta and y is equal to r sine theta. So they are converted and back. But what's important is that no matter what it is, if you have fixed a moment of time t and you apply these functions r of t and theta of t and have a point on the plane, or you apply x and y which are related to r and theta this way, using exactly the same moment in time, we have the same point on the plane. It's just two different views onto the same physical reality. Which means what? Which means that everything which we calculate based on these functions must be, if it's a physical reality, for instance, kinetic energy, it must be the same. So kinetic energy as a function of r and theta, as a formula, looks differently than kinetic energy of k of x and y. But if you will put one particular element, one particular moment in time t, into this, and have a value of r, and have a value of theta, and have a value of x and y, which are related to this, you will get the same results. They should be equal to each other, because it's a physical characteristic which is independent of our view. Mathematical representation as functions of these coordinates is our view, observer's view onto the movement, which has basically nothing to do with the reality. Reality exists without our intervention, doesn't really matter how we view and how we represent this reality. These are two representations, of how we quantify position in the space. Position is the same, it's a reality. And not only the position, but also certain functions related to motion, like potential energy, kinetic energy, or or magnitude of its linear speed, for example. It's completely independent. It's a physical reality. So no matter how we calculate it, using these functions or these functions, they are supposed to be exactly the same. And by the way, in the notes for this lecture, which I mentioned in the beginning, I have an example actually, polar coordinates versus this, and I calculated, I think, square of magnitude of the linear speed. And it looks differently, obviously, in polar coordinate than, but if you will put the values and real transformation like this, and expression of, let's say, I think v square as a function of x and y, and then you have v square as a function of This is Cartesian, this is polar coordinates of r and theta. So if you will do all these calculations, you will express it, and then you will use the transformation formula, put it here, you will get the same thing as here, obviously. So results will be the same. Okay, so that's it. This is all little things which I wanted to present to you. So probably one of the most important is the last one, transformation of coordinates. That's very, very important things. That physical reality is one thing, and our view is basically our view, and they must actually match. No matter how we view, we have to have the same physical number, the same from both viewpoints. Okay, so that's it. Thank you very much. Read the notes for this lecture, and good luck.